seems higher on 5K. I didn't do that. That's just the same.
Any questions about any of the problems I've given you guys? Are you guys keeping up? I'm about to start chapter 3, and by the time we're done with the material for chapter 3, be ready for the test. So, if you're keeping up, you're probably in pretty good shape. So here we are, Tuesday the 4th. It's 2 weeks from today that we'll have test 1. And I think today and Thursday, and probably some at Tuesday, we'll finish this chapter, and then Thursday we can review. Thursday the 13th, we can review, and then test on the 18th. Are you guys comfortable with what we've done so far? Even the electron configuration stuff? All right, so let me outline something as we start in chapter 3. Chapter 1, math stuff, if I want to rename the chapters. Chapter 2 was about atoms. Atoms, the periodic table, the structure of atoms, including the specific structure of the electrons on the outside. And really, we do this next. Chapter 3, where we are. Chapter 4 is really next test. So chapter 1, chapter 2, chapter 3 will be this test. Ions. So this chapter is about ions, aka ionic compounds. Chapter 4, which won't be until the next test, is about molecules. Which are molecules. Molecules is really a synonym for covalent compound. They're even sometimes called molecular compounds. If I really wanted to point out the difference, I would say, what was I going to say? Oh, the bonding. Really, the origin of these words, ionic compounds, and covalent compounds, that is molecules, is what's causing the bonding between the atoms. So first chapter, we talked about a bunch of math stuff. Second chapter, we introduced atoms. The next thing to talk about is how atoms come together into what we call compounds. The two major compound types that we study are ionic compounds and covalent compounds. There's also metallic, which we don't talk much about, but I'll just do this. And there is one more called coordinate covalent, but it doesn't come up in many contexts. So on the periodic table, you can split it between metals and nonmetals. Ionic bonding is always metals. That's always metals and nonmetals. If you've got a compound where atoms have come together and some of them are metals and some of them are nonmetals, then ionic bonding took place. If you take atoms off the periodic table and you only take the nonmetals, things made up of nonmetals, only nonmetals go into those types. And metallic, only So just to give you sort of an overall roadmap, and metallic bonding won't have its own chapter, but this is really where we are. We're getting to ions and ionic compounds. So right at the beginning of this chapter, it says Introduction to Bonding. And it's almost like Introduction to Bonding should have been at the end of this chapter. And then here's the things you can get when you do bonding. But it serves as an introduction. So bonding, atoms coming together. In bonding elements, gain, lose, and share electron. Okay, gaining and losing electrons is about ionic compounds. Sharing an electron is about covalent compounds. So really, we're going to talk about ionic compounds, all this chapter, but just kind of as a general roadmap. That helps to kind of put something in your head. So we're all in here, this chapter, and running up on the chapter, running up on the test one. We'll start with chapter 4 for test 2. So maybe all this is worth reading. Two different kinds of bonding, ionic and covalent. This statement really isn't true. I'm always catching textbooks out, but there's at least 4 different kinds of bonding. These are just the 2 major ones, at least as it's taught in chemistry classes. There's metallic bonding and there's also coordinate covalent. Covalent bonds, we won't say much about it. But if you just wanted to look at something and say, predict whether these are ionic or covalent compounds. You move that to the side. Tab 2, all you're looking at here, if you want to decide whether these are ionic or covalent, carbon and oxygen, those are both nonmetals. So is that ionic or covalent?
Covalent.
It's that simple. Calcium is a metal, it's over here. Fluorine's over there, nonmetal, so that's ionic, yes. Magnesium and oxygen, there's magnesium, there's oxygen, so that's ionic. Non-metal, covalent. HF would be ionic. No, that's covalent, because hydrogen really belongs with the non-metal, and this is covalent. So you're looking to see if it's got metals and non-metals. If it does, it's ionic. And all non-metals is covalent. Okay, to talk about ions. Okay, cations are positively charged, anions are negatively charged. Positively charged ones are the metals, and when non-metals become ions, they're the negatively charged ones. And I think it's best to introduce this by looking at the electron configuration of some of these. If we're going to do electron configurations, it's 1, 1, 3, 1, 3, 5. If you can do 1, 1, 3, 1, 3, 5 real quick, you can do that with off the periodic table, but if you just memorize that much, you can get this much. Remember, there's one more 1 right here. These are 4, so the 4s starts here. This is 2. We get to 3 where you have 3p. And this is the 3d. And let's start with something like nitrogen. 7 total electrons, 7 total protons. Really, the 7 means protons, 7 protons. For the neutral atom, let's just do neutral nitrogen. 7 electrons, 1, 2, 3, 4, 5, 6, 7. The charge, so there's neutral nitrogen, and then there's charged nitrogen, which is ionic nitrogen. So we're going to talk about the ions this chapter. Electrons tend to pair. Their most stable way to exist is paired. So if you bring in 3 new electrons, so it's neutral now, it's got exactly as many electrons as protons. I'll say 7 protons, there's the nucleus. It's got 7 electrons, but if it gains enough electrons to have all of its electrons paired, if you're just looking at this configuration, you can go, okay, here's what I need. I need 3 more electrons, then all the electrons are paired. Those 3 extra negative charges makes nitrogen a 3 negative. It's got, nitrogen is 3 negative, or negative 3. We usually write the negative after the number in chemistry. But the quick way to do that is to point at nitrogen on the periodic table and go 1, 2, 3. It's going to be 3. What I've done by adding 3 electrons is it basically has now the electron configuration of neon. But neon's neutral. Neon has enough protons to balance all these. Neon has 7, 8, 9, 10. Neon has 10 protons and 10 electrons, and it's got all of its electrons paired. In fact, it's got this, what we call the stable octet, 2, 4, 6, 8. The S in the P is full, means 8 electrons. We call that the stable octet configuration. All the noble gases automatically have that. But this stable octet is what's being achieved when ions, when atoms become ions. So carbon would gain 4, 1, 2, 3, 4. Oxygen would gain 2, 1, 2. Any of the halides would gain 1. In any of those cases, you end up with this stable octet arrangement. Stable octet, okay. Gaining electrons is what nonmetals do to become charged. They become negative by gaining those extra electrons. If I did, we're going to do nitrogen, beryllium over here. So 4 electrons. 2, 3, 4. There's beryllium. Now we're talking about metals. 4 protons, 4 electrons. Well, let me not start with beryllium. Let's go one below there, magnesium. Here's magnesium. 2, 4, 8, 10, 12. Yep, 12, okay. So there's neutral magnesium. When magnesium becomes an ion, it loses enough electrons in this valence shell such that it's got that stable octet in the shell just below it. So magnesium will lose those 2 electrons. So now it's got 10 electrons. So it's got 2 extra protons. So magnesium is 2 plus. And this is true of all of these. All of these, you start adding electrons, you'll get that stable octet, and then you've got an ion. When it's metals, it loses electrons, but ends up with a stable octet of the layer below it, thereby becoming positive. So it's this thing about unpaired electrons that want to be paired. So nonmetals have the capacity to gain some electrons. Metals can lose some electrons and still end up being very stable because of that stable octet configuration. Okay. The simple way to think of it, like I said, just point at the hierarchic table and count, but that's what's going on. And this is really easy. Everything, kind of ignoring hydrogen, but it can do this too. From lithium on down, those will all be +1. Anytime any of these are ions, they'll be +1. Here, these will all be +2. There's really only one +3 to think about. This will be +3, 1, 2, 3. That's on the metal side. So I told you to think of everything down this stair step as metalloids, and I kind of ignore those just for the confusion they might cause. But aluminum and polonium are the only two that are considered metals and not metalloids. So if these are metalloids, going down this diagonal, it's really everything from carbon, selenium, ion, phosphorus, over, and we can really ignore these. So there's only a small set of nonmetals that we tend to work with. It's fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, nitrogen, phosphorus, and carbon. It's really just those, and hydrogen. Those are really the only nonmetals we deal with. So all of those have very definitive charges. Carbon, if it's charged, it'll be -4. Nitrogen, if it's charged, it'll be -3. Same with phosphorus. Oxygen, if it's charged, it'll be -2. Same with sulfur and selenium. Fluorine, if it's charged, it'll be -1, and so will all of these down the iodine. These won't become charged. And these, like I said, these will all be +1, these will all be +2. So what about all the other metals? All the transition metals, and then all these metals down here that are not metalloids. And really all these down here, but we literally just don't talk about those. They're just too rare, too weird, too odd. So everything from here into the transition metals. What about their charges? Well, the weird thing about those are they can have more than one charge. You're not to go around trying to memorize it. It'll be sort of given in a problem to you. But it does mean something in terms of the ions and how you name them, and how you name compounds, and how you come up with ion formulas. If I broke down ions, metals become cations. Oh, I saw this in a meme the other day. Cat. They're positive. You ever seen that one? These are positive. And here's a pause. I can't draw. Anyway, that helps. All right, and then non-metals. These are always anions, meaning negative. You can break the metals down into main group. And really main group means these two columns and really just aluminum. Let's see, main group. And then plus the transition metals plus the metals below the so I'm splitting into all of these and aluminum into one group of metals, and another group of metals is the transition metals plus these below the metalloids. And what I'm getting at is I don't mean same charge with each other. I mean everything from this column will always, if it's an ion, be +2. No exceptions. And below hydrogen, these will always be +1. Aluminum will always, always, always be +3. The thing about these are, sometimes there's iron too, a +2 iron, and sometimes there's a +3 iron. So these have variable charges. So when I say same, I don't mean that they're all the same. It's just whatever charge I've told you those have. They're always that. But the transition metals plus these down here have sometimes +1, sometimes +2. Some of them have tons, like vanadium can take on just about any charge. +1, +2, +3, +4, +5, +6. And exactly why that is, I won't go into. But just knowing that helps you differentiate those for naming. All right, I'm going to try to get to the polyatomic ions, but there's 3 different types of ions. I guess this is another type, but I'll just leave that one there. These are, here, let me do this. Always have same charge. Same with these, always have the same charge. Meaning carbon is always, 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 if it's an ion, -4. Nitrogen is always, always, always -3 if it's an ion. -2, -1, always. But these are the ones that are variable. Polyatomic ions, these have very definitive charges too. But I'm kind of leaving those in another category, but let me explain what they are. And then I'll just stick with the ones from the periodic table, these 3 groups. But I told you that it's not until chapter 4 that we talk about molecules. What's a good example? Let's do sulfate. We will get to when we get to chapter 4, that's when you'll start seeing things like where we draw lines between the atoms. If you take it in chemistry class before and maybe just popular culture or something, you might have seen molecules drawn this way. This is C2H6. So that's the formula, but that's kind of a picture of the molecule. This is how things are connected up in this molecule. And that's what polyatomic ions really are. Polyatomic, many ions, I mean several atoms. Here's a polyatomic, but this one's neutral. If I drew, we usually put a bracket around it when we're putting a charge on it. So sulfate, I was looking for this picture, make sure I got the bonds right. So this ends up being a little negative over here, a little negative over here, 2 negative spots overall. That molecule, AKA polyatomic ion, is deficient by, or has 2 extra electrons in it, meaning if you added up all the protons in all these atoms, and then you added up all the electrons in all these atoms, you'd end up with 2 extra electrons. So that's what a polyatomic ion is. I might get to those, but I kind of leave those to the end of the discussion of ionic compounds. So this is not a polyatomic ion. This is a molecule that it has exactly the same number of total protons and total electrons. This is a molecule, and it has a total number of protons, 2 extra electrons if you compare them to the number of protons there. So that's a polyatomic ion. That is not, that's merely a molecule. This is still a molecule, it just happens to be charged, so we call it a polyatomic ion instead of a molecule. All right, so that's, in some sense, we're breaking into chapter 4 when we talk about polyatomic ions because we're looking at molecules. But it's the fact that the molecule is charged that we need to talk about it. And the formula here, we would write the formula that way, and we'll work with these a little bit as ions. But most of what I say is easier to understand if I just stick to the main groups and the transition metals, and then the negative non-metal ions. So just to break down, where do I go next? Okay, cations and anions. Come back to properties. Metals. Group number, ionic charge, I talked about that. I told you this, these are all positive 1, these are all positive 2, this one's positive 3, and then those negative ones. It's a good diagram of what I just said, and this is sort of diagramming the fact that you get more than one charge. I see frequently that zinc, cadmium, and silver, these three right here, I see frequently in textbooks that these are exceptions to this rule, meaning they really only take on these particular charges you're looking at here. That's not strictly true though, and I don't know why they carve out these exceptions. It is very rare that these have other than these charges, but the fact that they do, I don't know why they would act like those are exceptions, just because they do. Anyway, so think of everything down here and everything over here as having variable charges. That's important for naming. So I'll get there, naming ionic compounds. All right. So in covalent compounds, in molecules, they're sharing electrons. That's not the same thing that happens with ionic compounds. If I just use a very simple example, NaCl, sodium chloride. Chloride gains an electron and becomes 1 negative, chlorine. Sodium, Na, loses an electron as positive. You can picture it this way. You can picture a neutral sodium atom losing an electron, thereby becoming positive, and then that electron joins the Cl, making it negative. Truthfully, that's not usually how we get ionic compounds. They usually come, they've existed for millions of years, and we dig them out of the ground as minerals, and usually they come to us already this way. But you can do this as an experiment in a lab. This is called electrochemistry, where you can force that to happen. So you can think of it as the sodium losing 1 and the Cl gaining 1. But in terms of a formula, there's formula and name. So really kind of the way you would get this question is if I've got sodium and I've got chlorine and they react and make an ionic compound, what's the formula and what's the name of that compound? Oh, and let me say this. After showing you this, this is what molecules look like, and they're very different things than ionic compounds. If I had a sample of this is ethane. If I had a sample of ethane, I would really have a ton of these together in, say, a beaker or something. But if you have an ionic compound, what you've got is, I think I said this already, here's the context that really comes up. I just alternate like this, and I just continue building out, like I put another sodium here, and chlorine, sodium, chlorine, and here I put another chlorine, sodium. I could build this out this way, and I could build it out this way. You see what I'm doing, I'm just alternating them. And that's 2 dimensions, but I could make this 3-dimensional by putting a sodium atom right here in front of this chlorine, and then I'd have chlorine, sodium, and then a chlorine, and a sodium, and a chlorine, and a sodium. What we call that is a 3-dimensional lattice. This, if you zoomed in and looked at the structure of any of these ionic compounds, they form these lattices and they can get very big, make a big chunk, We call them grains. You've actually seen these before. If you pour table salt out, you see those little grains. Those are just large-scale lattices of these. Molecules can do this, but we would just say that's a solid rather than an ionic solid. You can get ethane to, but you'd be lining up molecule to molecule to molecule to molecule to molecule instead of individual ions. And these are being bonded together. We don't usually draw them as lines, but they're bonded together with ionic bonding. And ionic bonding is this already exists as positive, this already exists as negative, and then what pulls them together is those charges. That's different from the covalent compounds that the atoms pair their electrons and then make those little units called molecules. So these are huge crystals, where molecules are just little molecules. The formula here, we need to balance this out to make neutral, to make it neutral. And in this case, without any ones or twos or anything here, just one sodium and one chlorine gives you a balanced formula. And the name here is, that's chlorine from the periodic table. You swipe off the I and E and you go IDE, and that's it. You leave the cation alone, just the name off the periodic table. And then you put IDE. So when it comes to, like I said, there's only a few nonmetals that we deal with, and here's how those go. If it's carbon, it's carbide. If it's nitrogen, it's nitride. Oxide, fluoride, phosphide, sulfide, chloride, selenide, bromide, and iodide. No, iodide. So you just add 8 IDE to the end. You take the I and E off and you put IDE. Here you take IUM off and put IDE. Sulfide, take the FUR off and put IDE. So that's how you name these. So the positive ion is the same name as off the periodic table. The negative ion, you take off the end and you put IDE. So that would be called sodium chloride. Another example, if I said if we had what's a metal? Lithium and oxygen. And your question was, okay, what is the formula and what is the name when you take lithium and oxygen and make an ionic compound? What's the charge on lithium? It's on the left, near the top. +1. For some weird reason, we leave the ones off in chemistry. I don't know why. I could put 1+, but we always just leave the number off when it's a 1. Oxygen, what's its charge? Minus. So to make these charges balanced, if I had 2 positive charges, I would balance the 2 negative charges. So the formula is Li2O. Really, I mean Li2O1, but like I said, again, we tend to leave the 1 off when there's just 1. That would be the formula. The whole point is to make the charges balanced. We sometimes call this, instead of a molecular formula, we call it, I forgot what we call it, just to differentiate, because we don't mean there's literally 2 lithiums and 1 oxygen associated. It's just a ratio in that big matrix, that big lattice. The ratio in that big lattice is for every 2 lithiums, there's 1 oxygen. When it was in ACL, it was 1:1. In this case, it's 2:1 in that big lattice. When we give a molecular formula, we're literally saying that little unit has this many of this. That doesn't just mean the ratio of carbon to hydrogen is 2:8 or 1:4, whatever it is. We mean that there are little units like this in the sample. That would have been a 6. C2H6. So 1:3 ratio, I guess, if you've got a beaker of a bunch of these. But really, the formula here is referring to the molecule that literally has 2 carbons and 6 hydrogens. Here, we're not saying every little bit of the sample has 2 lithiums and 1 oxygen. We're saying that's the ratio in one of those little crystals. So that would be the formula here. And the name. It's lithium and oxygen, but you don't say oxygen, you say oxide. Don't mess up and think that this is dilithium monoxide or dilithium oxide. We don't use di-tri, mono when we're naming ionic compounds. These types of prefixes don't show up in this chapter at all. Ionic compounds, because the point is, there is only one way that lithium oxygen can come together, because lithium is always going to be +1 and oxygen is always going to be 2 negatives. So a chemist knows what lithium oxide means. They know what you're saying. Let's contrast that though. This was part of the main group. Main group, I mean, these 2 columns, not counting hydrogen, but I would throw aluminum in as well, and I guess polonium as well. No, polonium goes with these down here. Aluminum in those 2 columns, if it's any of those, it's just this and it's very simple. If it's one of those with variable charges, I like using, let's do iron and oxygen again. All right, so and again, you don't have to memorize the various charges, like iron can be 3 or 2, +3 or +2. You don't have to memorize that, you'll be told from context. But let me just point out, there's such thing as iron 2+, and there's such thing as iron 3+. So it has to be specified. Let me do the Fe3+ and oxygen. All right, so the formula here, what's the charge on oxygen? 2 negative. We only need one of each of these to make those charges balance. So that would be the formula for this one. FeO, if you want the name of it, you say iron 2 oxide. It's iron oxide, but in the parentheses, you've got to say what the charge is on iron. Another word for it is oxidation state instead of charge. Those are very closely related concepts. So the book might say oxidation state, I'll just say charge. But this is saying the charge on the iron. And this over here, when it's +3 or -2, or -3 and +2, coming up with formula is a little bit tricky, but it's sort of like least common multiples. If you want these to balance, I'm going to need 2 irons and 3 oxygens. That way both of them add to 6. 2 times +3 gives you a +6. 3 times 2 negative gives you -6. So you have to have 3 oxygens and two irons to make that balance. It's only one that's tricky at all. I suppose that's not true because you can get really high oxidation states out of some of these, like a +6 and +7. But in most cases, that's the hardest. But you sort of have to do what's the least common multiple of 2 and 3. And you come up with 6. So then you go, okay, this has to add to -6, and this has to add to +6. And this one would be called what goes in the parentheses? So 3, Roman number 3, Roman numeral. So like if I sent one of y'all at Stockton and I said, give me some iron oxide, you'd head out And then you have to stop and think, wait, which type of iron oxide does he want? Does he want this or does he want this? Does he want iron 2 oxide or iron 3 oxide? But if I sit and you do the stockroom for some lithium oxide, I wouldn't need to specify anything because lithium is always +1 and oxygen is always 2 negative. But iron is not always a particular charge. So you have to put the parentheses. So those in the transition metals plus these down here, those you have to put a parentheses in the charge. But you don't have to memorize these charges. They come up in context. Let's see. So formula and naming. Let's see what I've got. I did make some of these problems in the book. I mean, on under assessment quizzes. And I think we can do these just based on what I've said so far. Formula for ionic compounds. Polyatomic ions might come up in some of these. So maybe I should do that. Okay, polyatomic ions. Remember that those are, polyatomic ions are molecules. So you'll see a full formula for them. But, okay, so main group metals, transition metals, and the metals underneath the metalloids. And then the other type of ions, the polyatomic ions, don't worry about their structure. But this list I'll give you on the test. It's just a matter of being able to pick them out. But most of them are negative. There are a few positive ones. We didn't put any positive ones on there. But almost all polyatomic ions are negative. Here's an exception. So notice all of those are negative. There's a few positive ones. I'm forgetting one, I think. Anyway. So, for example, CO3. So you've got the names, the formulas, and the charges on them in this chart. Carbonate, what should I do here? So what's the charge on aluminum? It's 3+, you can get that from the periodic table. 3+ and 2 negative, so we're gonna need Al. You put the parentheses around it, and then that 3 means there's a total of 3 of these CO3s. So you got a total charge of -6 and a total charge of +6. That's the formula. And then the name, straight off the periodic table this, and this is carbonate. Carbonate you can get off of here, and the charge on CO3 you can get off of here. The tricky part is picking these out of a formula. When there's not a parentheses, let me do one like that. One of these chart. Let's do aluminum phosphate. So if I said I've got aluminum and phosphate, so you get the formula off this chart and the charge off this chart. PO4, 3 negative. Off the periodic table, you can get 3+, and you go, okay, they're already balanced like that, so I just need aluminum. That's the formula. Because there's only one of these, I don't have parentheses with a number subscript. And that's the tricky part, but you can see the metal easily. So that tells you the rest of this is a polyatomic ion. So seeing them in the formula, it's only tricky when this doesn't have parentheses, when there's only one of them. Here, it's easy to see that the anion is in parentheses. And the name of this what about so iron phosphate, this is necessarily 3 negative. And let's say it's iron 2. So this one would be Fe3. And what goes in the parentheses? 2. Don't be tempted to do this. That's how many irons are there. It's this, the charge on the irons that we want there, 2. I'm always tempted to. I don't think your book does that. I think those are called titles or serifs or something. Anyway. Iron 2 phosphate. You good? It actually covers a lot. Let's see about answering some questions. So I'll give you all this on the test. Let's do naming ionic compounds. These questions, they put this weird little space in a lot. I don't know why. I could go through and edit them all, but hopefully you see that's SNF4. If you found SN on the periodic table, it's down in the variable charges. Since SN is down there in the variable charges, what's the charge on SN? I told you don't have to memorize these, but you can get them from context. First of all, what's the charge on fluorine?
-1.
So you're looking at the periodic table, that's what you do. You look at the periodic table. What's the charge on oxygen?
-2.
-2. So what is fluorine?
-1.
-1. There's 4 of them though. So that means there's a total -4 charge in this formula. That tells you that this one SN atom must be +4. So you'd have to say here 10, and I guess you do IV, capital IV. Fluoride. That would be the name of this. You would have to put the parentheses because of SN is down here. So it's got a variable charge. I guess that accepts it as correct. Let's just see how the answer here looks. Sometimes they capitalize things and it'll count it wrong. Don't worry about capitalizing. I'm probably going to do all multiple choice on the test. Oh, they're using a different naming scheme here that I didn't go into yet. All right, well, the way I named it is correct for the naming scheme I have taught you so far. Maybe I should delete those, but I intend to get to that eventually. Oops. Report together, dude. Preview. Start quiz. So I guess don't worry about that one. This is just saying ionic bond between the metal on the left side that'll count correct. All right, here we go. Potassium and iodine. And it's giving you the formula Ki. I know it looks weird, but that's the formula for this compound, Ki. Ki is added table salt, blah, blah, blah. What is the name of this formula? So what is the name of this? K is tricky, that's potassium. Potassium what?
Iodine?
Not iodine. The negative one, what is it? Iodide. I think it counts this one wrong because it capitalizes the P, but don't worry about that. So which pair of these will make an ionic compound? Are you lost suddenly? What is it we're looking for ionic compound? We're looking for a non-metal and a metal. The first two, sulfur and oxygen, those are both non-metals, so not that one. Copper and iron. So the first two, sulfur and oxygen, you can put those together and make a compound, but it'll be a covalent compound because it's got covalent bonding, sharing of electrons. Copper and iron, you can put those together and make a compound, but those are both metals, so you'll have a metallic compound, also known as an alloy if it's a mixture. Iron and chlorine, metal and non-metal. It's the only metal-non-metal pair in this list. Bromine and oxygen, you can put those together to make a compound, but that'll be a covalent compound, sharing of electrons. Magnesium and lead, both metals, you could put those together and make a metallic compound, but not an ionic compound. And we're talking about ionic compounds here. So that's what you're looking for, metal and non-metal. Okay, what is the formula between potassium and bromine? What's the charge on potassium? That's K on the periodic table. We're here, potassium. So what's the charge on potassium?
Awesome.
Yep. And what's the charge on it says bromine. We're gonna call it bromide, but that's over here. What's the charge on
Negative one?
negative one? So it's just a one-to-one formula. So it should just be KBr. Potassium and bromine, KBr. What is the proper name for CuCl? So they're showing one copper and one chlorine. But copper is a transition metal, so it's gonna need the parentheses. But if there's just one copper, that's the formula for it, but what's the name for it? If there's just one copper and one chlorine, well, you start with the chlorine, you start with the non-metal. And you go, chlorine is gonna be a negative one. That means that copper is a positive one because of the formula. There's only one copper there and chlorine is one negative, so that copper has to be, so copper can be +1 or +2. In this case, it's +1. So this is what you've got to put. There is such thing as copper 2 chloride. That would be CuCl2, because it would have two negative charges to balance the two positive charges. Does this make sense? But this one's copper 1 because there's only one negative charge on it. Make sense? Magnesium fluoride. Or I just gave you the name. But which of these down here is correct? Let's call them A, B, C, D, and E. Which one is correct? A, B, C, D, or E? C says magnesium 2 fluoride. You just got fooled though. Magnesium only ever has +2. So you don't need the parentheses. This is properly just called magnesium fluoride. If I say go get some magnesium fluoride from the stock room, there's only one compound on the planet in the universe that is magnesium fluoride, because magnesium is always 2+ and fluorine is always 1-. So MgF2 will always just be called magnesium fluoride. There's no variation. This is sulfate. If you looked it up, maybe I shouldn't have this question here because I'm just going to give you the formula, the charge, and the name. So this is sulfate ion. Sulfide, sulfite is also in that chart. Where is that? Sulfate is SO4. Sulfite is SO3. They're both 2 negative, but they're both in this chart. So you would just look in that chart and look for sulfate. What is sulfide? Here's sulfur. What charge will it be if it's an ion? -2. Everything in this column, aka group, is -2. If you have sulfur and it's gained 2 electrons and it's 2 negative, then it's called sulfide. So if you look in that sulfide, sulfate, sulfite. I don't know if I put bisulfate or sulfoxide. Bisulfate in here. Yeah, this is bisulfate. I said none of those would show up. Di, tri, tetra. This is the only place it shows up. It's kind of weird, but there's 2 ways you can name this. You can call it hydrogen sulfate or bisulfate. And you can call this one hydrogen sulfite or bisulfite. This one the same way. There's dihydrogen phosphate and there's hydrogen phosphate, sometimes called biphosphate. But just go by what's in that chart. We're kind of getting into the weeds with all of that. So what's the formula for, this is 10,4 cyanide. And cyanide's in here, I think. Yeah, cyanide. Carbon and nitrogen together as a molecule, charge -1. So which one of those is correct? For 10,4 cyanide. Cyanide is 1 negative. C, yeah, that's correct. It's this one. 10 has a charge of 4 plus 4. We get that from here. And cyanide has a -1, so you need 4 cyanides to add up to -4 to balance the 4. You see that? All right. Ammonia, it's mentioned in the chapter, maybe just write it down. The NH4 is ammonia. Since it's not in that chart, you might write it down. This isn't going to show up in any of our compounds. H3O, hydronium. The H3O shows up a lot in coordinate covalent compounds. I've said there's ionic, covalent, metallic, and the 4th one is coordinate covalent, but we won't cover those. And I'll mention here, there's 2 of these because they're +1. So you would say ammonium. And the SO4 is the sulfate. But again, you're not going to say diammonium sulfate. You just say ammonium sulfate. Ammonium sulfate. Here. Just because NH4 always, if you're looking at this, a chemist knows that NH4 is +1. It's never going to be any other charge. So you don't have to say di and you don't have to put anything in parentheses. Ag is silver. This is one of those where they don't use, I'll always do it where anything from here all the way over to here. I won't put any of these weird exceptions. Like zinc tends to have the same charge always, but there are exceptions. Cadmium tends to have the same charge always, but there are exceptions. Silver tends to have the same charge always, but there are exceptions. I don't know why they point these out and say that they don't have variable charges, but a lot of textbooks do that. I think it's silly, so I'm just not gonna put those on the test. So if it's any of them in there, assume it needs a parentheses. It's only those three that anyone ever makes exceptions about, but I just won't put those on the test. And I think they do that in this textbook, so. We'll look at the answer key, but I looked at this earlier and it seems like they did this. I would say silver 2 oxide. Because O is 2 negative. Oh no, this would be, I would call this silver 1 oxide. I want an example like that. Let me see. Let me make up my own. Well, let's finish this. We're almost done. I would call that silver 1 oxide. Let's see what they do. AU is gold. So if they give you this as the formula, and gold is down in those variable charge ones, so you want to use a parentheses. What's the charge on gold here? If there's 3 iodides, what's the charge on iodine when it's a here's iodine, so what's its charge? -1. And if there's 3 of them, I don't know why there's a space here, but if there's 3 of them, that means there's a total of 3 negative charges there. That means the gold has to have 3 plus charge. So gold 3 iodide. The name 2 and the name lead acetate specifically indicates that there are 2 lead ions present in the compound. Is that true? It doesn't refer to the number of lead ions. It refers to the charge on the lead ions. So that's false. HPO4, that's in here. HPO4 is hydrogen phosphate. So this should be calcium hydrogen phosphate. There's actually the word hydrogen in here. The name of HPO4 is hydrogen phosphate. So you would just write hydrogen phosphate instead of just phosphate. So that's false. Let's see how I did. Let me answer the first one. There might be spaces here, I don't know, they might capitalize the T, but don't worry about odd little things like that. Oh yeah, that's right, they used that different naming scheme. I'll come back to this naming scheme, but just don't worry about those types. This is legitimately called tin-4 fluoride. The stannous fluoride, the stannic fluoride is a different naming. You can use stannic or stannous, and that's referring to 2 different charges, but I just feel like you should probably know those, so I'll try to squeeze them in later. And yeah, they're assuming silver. Silver is down in this part of the periodic table. It's right here among these 3 in this little corner. There's silver. But like I said, I just won't put these on the test. But there would happen to be one. These questions I get, I download from the publisher's website, so they have stuff in there that I have to catch. So on a test, I just won't put silver, but if it's me, I would say silver 1 oxide, and any chemist would know what I mean. There are very rare things, rare compounds that it's believed that silver has a different charge. So. All right, let's look real quick. I've got another section I think you can do that's more about building formulas. And I've got a few minutes. Let's just do a few of these. iron 3 bicarbonate. Bicarbonate, HCO3, and it's -1. I guess they just want you to write a 3. You can't make a subscript here. So we're pretending that's subscript. So that's the negative ion. If it's iron 3, that means it's Fe, and it has a charge 3 on it. If the bicarbonate has a charge -1, there have to be 3 of them. I want this, I'm trying to write this. I guess we should see what the answer key does. I'm trying to write it. I'm trying to do that. So it's 3 HCO3s with 1. I guess I better look real quick. How it deals with subscripts. That's literally what I have, isn't it? FeHCO3. Counted it wrong, but these aren't for any points, so you can look at the answer key. HCO3. Yeah, I literally have the same thing they have there, but it's counted wrong. But just, use your brain when you look at these in the answer key. Let me just give you one more made-up example because I haven't found one. And then I'll leave you those to practice. It's mostly about coming up with the correct formula based on charges and coming up with the correct name. But what if you had, what am I thinking here? Six. All right, and I said, come up with the name of this. And you would probably go iron, something, and I'm trying to figure out what to put in here. The charge on oxygen is definitely -2. If there's 3 of them, then you have a total of -6. So you have a total of -6 from the oxygens. That means you're gonna have a +6 over here. But you've got 2 Fe's. So you take that +6 and you split it into those 2, because there's 2 of them. So this is +3 and this is +3. So that's iron 3 oxide. Sometimes you have to infer the charge on the variable charge one, and it's easy if there's just one of them, but if there's several of them, you're gonna have to, you find out how many total negative charges you have, and you automatically know that's how many positive charges you have. And if there's more than one, you have to split those charges into those to figure out what the charge is on this. See what I'm saying? Kind of circuitous route, but you can do it. If there's only one of these, it's very easy. If it was this, that's still iron oxide. So you would go, oh, that's 2 negative. That means I have to have 2 positive from this side, but there's only one, so that's 2 positive. So then you could easily do that. But when it was Fe2O3, I had to go, okay, I have a total of -6, and I have +6, but I've got to split that +6 up between 2 irons, and that's how I came up with 3 plus and 3 plus. And that's how I came up with a 3 there. See what I'm saying? If there's more than one cation, you have to split the charges up among them. But that's easy enough to do. Just realize you have to infer that sometimes in these questions. All right. I've opened 2 of these quiz sections, and there's a lot of questions in each one of them. So you should see naming ionic compounds and formula for ionic compounds. You could probably do this one too. About electrons and configurations, sort of. All right, so try those just to stay current. And if you're keeping up, the rest of this chapter should just kind of fall into place. That's the bulk of this chapter. Ions, the different types of ions, the naming, balancing formulas. All right, are y'all good? All right, email me with questions. Some people email me with questions. If you've got questions and I can answer it by email, go for it. And